So here I will try to discuss some properties of the residue maps for a discretely valued field. So right. So I'll begin with the construction of the so-called Serre residue map. So that will be my goal for the first part, Serre residue map. So to begin with, uh, right. So what we'll do is, so the basic idea is if you have an integer n that is co-prime to the characteristic of the residue field little k, then we need to define. So actually we'll define the map from here to this. So this is the usual notation of the Galois Cohomology maps. Okay, and then we also have that isomorphism uh, of the intorsion part of the Brar group, which comes from the Comet theory. Right. So to begin with, even before we begin, let's just write two formal statements that we'll need. Proof of them are kind of easy, but let me just first write the statement. So let me just write these two theorems. So suppose I have a profinite group G, so which mostly will be absolute Galois group of the big field, capital K here, and you have a closed normal subgroup, and then you have the quotient, which I will denote by gamma. So that will be my setup, and C is in a discrete G module. So C is in a discrete G module. Okay. So the first statement says, suppose hi of n comma c is 0 for all I at least 2. Then I get a then there exists a long exact sequence. Like so I'm writing the ith stage. So then the next one will be one lower, and the next one will be two higher. Now, so this will start for I at least 1 because you have I minus 1, so I should be bigger than equal to 1. And one way to remember is so if you look at the first few terms, it will start with h1 gamma with coefficients c power n and then h1 g c and all. So one way to remember is that's the part of the usual inflation restriction maps, right? So for I equal to 1, so at the beginning, so I'm writing at the beginning of this long exact sequence, it will be h1, then gamma is just g mod in cn, then it will go to h1gc, that is the inflation map, right? And then it will go to, if I is 1, that is h naught, meaning the invariant sets. Invariant set of what? This, right? Then it will go to h2, this, and so on. So that's the beginning of the long exact sequence. That's one way to remember. There is a restriction map, right? And and that is the so-called transgression map. Okay. And second statement kind of follows obviously from the first one, because suppose you have moreover, suppose n acts trivially and this is a split exact. This is split. Then what you get is pretty much clear. Split. Then for each, sorry, then for each I, at least one, you will get, so C power n is C because n is trivial unit, so everything is invariant under the action of n. You get this to this. Okay. So second statement kind of follows obviously from the first statement, right? Because you have a section of this map from G to gamma, you have a section in the other direction from gamma to G. So you will get those things. Now, so to show the existence of the long exact sequence in the first place, and that kind of follows pretty much easily from the following. So recall we have the so-called Grothendieck spectral sequence, and a special version of it is this Linden Serre Hochschild spectral sequence. So I'm not writing the Grothendieck version because I will just need this special version, which is basically the same if you put in the right context of the Grothendieck spectral sequence. Anyway, so this is just HP gamma HQ and C. This is the second term of this page, right? So that's the so-called PQ term of the second page, and this abutes to or converges to this. And you also have to use this fact that this is 0, right? So I'm just writing the second page. So let's see how to prove it. The proof is kind of easy, but it's kind of tedious also. So to begin with, so let's write page 2. Our convention is whenever I'm writing PQ, the first term indicates the column and the second term indicates the row. That's kind of opposite to the convention that we are used to, right? Mostly we use row to indicate the first parameter and column to indicate the second, but here we are using the opposite. And so on page 2, the arrows will go 2 right, minus 1 up, that means 1 down. And what's the first row? And this is the first coordinate spectral sequence. It will converge because as you go along for each PQ, as you go along to the uh, more and more deep into the book of spectral sequence, the arrows will get longer. So eventually for each PQ, there will be some stage where there is a 0 coming in. So at some stage for large enough page number R, there will be an arrow that's coming out of 0 to your ERPQ, and there will be an arrow going to 0. So from that stage onward, if you take the cohomology, nothing will change and everything will stabilize. So it's obviously convergent. It's the first coordinate. So let me just write the first coordinate. So that's just E 200. Then that is, so remember first entry indicates column, so that should be 10. It's 20, 30, and so on. So this one will be E2, and that is 01, that is 11, that's 21, that's 31, so on, right? And everything above it is 0, right? Because of this assumption that, uh, because of this assumption. So, and of course, everything below it and to the left of it and everything is 0 anyway. So, okay. So, and what about the arrows? So this will go to this, which I am calling it as D2. This will go to this, which I am calling it as D3, so on. So basically this numbering you can remember I am denoting DJ, that's going to E to J0 for J bigger than equal to 2. And for this first two entries in the first row is, so this will go to, and by the way, everything in the first row should go to 0 because there is all the zeros down. So that's, I'm not denoting them. And so this will, there will be an arrow coming from here to there, right? So this place is already stabilized. Same for this. There's an arrow going to 0 and there's an arrow coming from 0. Okay, two right, one down. Okay. So now let's just look at page 3 and that will pretty much give me what we need. So this is 3 right and 2 down, the bigradation of the maps. And so this term, so these two terms will be as it is, and the rest of the terms will be co-kernel of D2, that's co-kernel of D3, and so on. The terms above it will be kernel of D2, that's kernel of D3, that's kernel of D4, and I'm not writing the other one, and so on. And everything else is 0 as usual. Okay, now observe that everything is trivialized here because you have to go 3 right and 2 down, but from each of the row, if you go 2 rows down, everything else is 0. So this is the final page. So you can also write it as the final page, also called the page infinity, right? Because obviously, because you have from this entry, if you go 3 right, which is kernel of D5, then you go 2 down, which is just this 0. So that's like mapping to here. And obviously, it's coming from a 0 because there is nothing above this row. So anyway, so that's this. So that's the final page. And now from the filtration and from the edge map, what you will get is, so you get short exit sequences of this type. So, so if you look at this, so you get a filtration of H1 like this. Okay. For the next one, I don't need the full strength of it, although let me just write it. So I am getting short exit sequence of this one. Let me write another one that will just co-kernel of D3 to H3 to kernel of D4. Okay, and we'll get so on. I'm not writing the other one, and now we just have to splice them up to get this required result. So let's start with this. So from the first short exact sequence, I'm just taking this. And remember, these are all split exact sequence because we have this filtration thing, right? So these are all not only exact sequence, these are all split exact sequence. So, right, so these are all split exact. And now, what we will like to do is, you have kernel of D2, right? Now, where does this object sits in? Kernel of D2 is somewhere inside this because D2 is the map that's going from this. So this you can inject it inside E2 uh, 0 1, right? So take the component. Now from this you have the map D2 that goes to E2 2 0, right? It's 2 0. Okay. Now you notice this fact that from E2 2 0 you can go to the co-kernel, right? Because co-kernel is just E2 2 0 modulo the image of D2, and so you can just, so this projects onto the co-kernel, and for co-kernel there is a map to H2 and so on, and that's your result, right? That's what the theorem on says. Because if you just put it into right context, what you will get is, what is the first term. The first term is just E2, so that's E2 1 0, so that's H1 uh, gamma this. Then that's the full this. Now what is E201? That is just this. Now what is E220? So 20 means just uh, so let's see. Alright, so that's just E220. So that is this, and 0 means E power n, and that it will so on. So at the highest stage you will get the exactly this. So that proves the first part, and second part follows obviously. Obviously follows from one. And also I didn't check one thing, that this after adding up this short exact sequence, the long exact sequence is, I mean, it's actually an exact sequence, which is kind of tautology, because although like all we have to check is the exactness at these points, because we have added or we have spliced up the short exact sequence at exactly these points. We have to check the exactness at this point, but that's kind of tautology, you can easily check it. Okay, so right, so that's about it. So we'll need these two results later. So let me just write it one. So we'll put G in gamma in a suitable setup, and in that setup, the assumption of the theorem one, that the HINC is 0 for I bigger than equal to 2, will automatically follow, and from there we'll get a long exact sequence, and also it will follow that this assumption of 2, that's this is split, will also follow, and n will act trivially on whatever the c will be. I'll come to it later. And from there you get this split exact sequence. For each I bigger than 1, we have the split exact sequence, and that is basically just the continuous homomorphism. And actually in that context, this map will be actually the residue map in that context. We'll come to. Okay. So now we'll come to the much more concrete setup. So far we have just some abstract assumptions and some results. So to begin with, uh, let me just write the setup first. Okay. So the setup is as follows. So this is done. Now so I'll begin with an Henselian discrete evaluation ring with its field of fraction capital K, residue field small k, and that will be my assumption throughout this upcoming uh, videos as well. And so clearly we have this tower of extension. So K sits inside its maximal unramified extension, that sits inside its maximal tamely ramified extension, and everything is of course inside the separable list. That's the uh, separable closure. So right. So unramified means L over K is unramified, meaning that if you look at the unique maximal ideal of R and look at the extension inside the OL, that's still a maximal ideal. right? So that means unramified. And tamely ramified means the ramification index of the same thing is co-prime to the characteristic of thing. So in that case, if it's something is unramified, that means anyway the ramification index is just one. So that will obviously be tamely ramified. So from there, and maximal unramified means we're just taking the direct limit over all such finite unramified extensions. Sorry, and same for tamely ramified. So that's denote. So KT is the maximal tamely ramified, and KNR is maximal unramified. So obviously this inclusion will follow, and rest of it is just obvious. Okay. So now some notations. So for throughout, G will be the absolute Galois group of K. Uh, Gamma will be the this Galois group, and that is basically isomorphic to the Galois group of K shape over K, the absolute Galois group, obviously, right? Because that follows from the definition of unramified extensions that the residue field extensions are still Galois with the isomorphic, and because we are taking direct limit over all finite separable extensions of the residue, we will get the full Galois. So, right. So moreover, I will be the inertia group, which is Ks over Knr. N will be my tame inertia group, and W will be my wild inertia. Okay. So this will be my notations throughout. Cool. So now, and by the way, all these materials, at least for this part, I think most of them you could find it in this lecture notes by that goes by the name the cohomological invariants uh, in Galois. So it's basically a lecture series. Uh, so there are three authors to it. Garibaldi, then you have Merkurjev and Serre. So I guess this can all be found in that book, at least for the first part. Okay, so now we'll try to prove the condition of those theorems so that we get the existence of the residue maps. Okay. So the first thing first, you have, so let's see how KT can be found by adjoining some elements into K. So to begin with, you just take a finite tamely ramified extension of K. So let L be finite tamely ramified extension of K now. So let's, so obviously the degree of the extension will be, let's call it E, and that's co-prime to the characteristic of the residue field by definition, right? So what you do, you choose an uniformizer. Let's say pi1 be an uniformizer. Then obviously we have pi, which is this, because obviously because you have the E is the degree, right? So that's also the ramification index. So if we start with the maximal ideal down states, that is inside K and R, then that's that's obvious, right? So and pi is an uniformizer in K and R, right? And now what you can do is you use a unit in L here, right? And then because you're working in Henselian, so by Hensel's lemma, U is an Eth power. That's basically from by Hensel's lemma. So you have x power e minus u, that polynomial, and you can just take its derivative and find a root. And because it's separable, because e is co-prime to characteristic of k and so on, so you can go to the residue field. It's separable there, so it's separable originally, and you will get this. So what you can do is, because u is eth power, so u is something power e. So as a whole, you can write pi as pi1 power e for some other uniformizer, right? Because you can take the product of pi1 with the of whatever the element that power e is u. So you can write this, and then by Eisenstein criteria, obviously you get k n then pi power 1 by, and that's structure of a finite time ramified expansion. So if you go to the direct limit of that, what you will get is kt can be found. So taking direct limit, kt can be found by adjoining an nth root pi n of pi. So pi is a fixed uniformizer inside k n in k sub such that, because if you take the direct limit, you need to have this compatibility relation that pi mn per m should be pi n for all mn, right? So that's what you get. And then if you just write, if you just denote k prime by the extension of k generated by, so that's the extension of k generated by all this pi n, then you get kt is k in a this composite field. So you have this short exact sequence, which is just, so gamma is what? Gamma is this. So that is split, right? Because you have a section in the other direction. Because if you start with an automorphism of k inner fixing k pointwise, you can get an automorphism of kt. What you will do, because so any element of kt is just some combination of k inner and elements of k prime. So you just send elements of k prime as an identity to the same element, and elements of k inner by way this the chosen automorphism of K in Rx. That gives a section of this third arrow in that short exercise. And obviously, by definition, N is the kernel. Okay. And then, oh, by the way, I forgot to mention one thing, I guess, because throughout I'm mentioning this characteristic of this thing. So anyway, so P will be mine. So let's write it there. So P is the characteristic exponent of K. So what does it mean? It means simple. It's kind of simple. That so if P is zero, then the characteristic exponent. Oh, sorry, if characteristic of K is zero, then this exponent is one. And if characteristic of K is something positive, then I mean the characteristic exponent that's that number itself. Okay, so it's kind of confusing, but yeah, that's how it is. So in case if so for a positive characteristic field, its characteristic and characteristic exponent both coincides. Otherwise, it's just one. That's it. So mostly you can just take the characteristic to be P, and in that case, both of them are same, and you can go through. Otherwise, it's just one. So we have this, and now that's a standard fact that the pth cohomological dimension of a field of characteristic P, which is, for this example, you can take the residue field as characteristic P, so its absolute Galois group has pth cohomological dimension lesser than equal to 1. That is my gamma. Okay, so what you get is, and that you can just write it as G mod this. Okay, and again I forgot to mention one more thing. So if characteristic of K is how should I say? So if characteristic of K is uh, right 0, so let's write it here. So basically I forgot to mention what this wild inertia group is, the W. So there are two cases. So P is my characteristic exponent. So it is 1 means the characteristic is 0, and else means the characteristic is P. Kind of confusing, I mean. So in that case you get so in that case that is 0, and in this case you get something pro P. Anyway, so obviously if you have a torsion G module discrete, so obviously if C is a torsion G module, so discrete torsion G module having no P torsion, it's a torsion but no P torsion, having no P torsion part, we get HI of W comma C is 0 for all I at least 1. That's again obvious because C has no P torsion, and W if it's 0 then done, otherwise it's a pro P group. So, yeah. And one can also show, not just proving it yet. So that's one fact. Another fact is, so this N, which is just the tame inertia group. So that's the direct limit of, oh sorry, that's the inverse limit of, right? Because how does the tame maximal tame inertia, tamely ramified distinction is defined? It's just K in a, then you are adjoining some suitable choices of some nth roots of a fixed uniformizer, right? So then in that case, this is the this. And remember the original field has nth roots of unity, right? or I'm sorry, the KNR has nth roots of unity because of Henselian's property. So we have this, but this inverse limit runs over all n such that this is 1. So in case if the characteristic is 0, that means P is 1. So every n will appear here and you will get just the usual profinite completion of Z. And in other case you get, that's also obvious because everything, so every natural number that has a prime factor P will vanish, will not appear. So you get Z hat mod some pro P. Right. Okay. And then again you can show from Serre spectral sequence that Hi uh, I comma C is 0 for I at least 2. So now you see how the conditions are getting satisfied. And that will basically follow from the Serre along with this fact that the cohomological dimension of n is at most 1. Because in the first case it's exactly 1, in the second case you can also show it at most 1. Because it's the quotient of Z hat by some property. So, right. So now, okay, so let's come back to the situation here. So we have a split uh, exact, rather short exact this thing sequence. You have a pth cohomological dimension less than or equal to 1. So from the characterizing property of uh, the cohomological dimension at most 1 groups, you get that, so you get, so let me write like this. So now remember you have W to, so W is what? W is the wild inertia, which is Ks over Kt. And you have I and N. So you have these two. That's again an exact sequence, obviously, right? Okay. So let's just verify it's obvious, right? Because right, I mod W is in. Okay. So that's this thing, and then you can show pretty easily that. So in case W is 0, then I and N are basically isomorphic. So if the characteristic is 0, then I and N are same. There's no wild inertia. So, all right. So now from a characteristic property which can be found uh, here, this says Galois Cohomology. So that's I think section 3 of chapter 1. There's some result, the characteristic property that uh, shows that you have, so remember you have homomorphism from gamma to G mod this, right? So there is a section. So this result S lifts to S prime, which is from gamma to G. Right. Because cohomological dimension of gamma is at most 1, the pth cohomology. So then, already we had this. Actually, I don't need it at the moment, so I'm just erasing it. So already we have this short exact sequence, and one can show that The map that we get here, this bar, that's actually a splitting of this map, the projection. Right. Or not projections, it's the surjection. So you get that is split. And now everything falls into their places because you have this, you have this. So what you do? You get residue maps, right? From theorem 1 because all the conditions have been satisfied. Theorem 1. So C is a gamma module of exponent uh, coprime to n. Oh, sorry, coprime to the characteristic of K. Then obviously you get maps from this, right? So by the way, I forgot to define this. So these maps, how are they coming? You just look at theorem 1. Everything is satisfied in the part 2 of the theorem. So you get some maps here. And that C minus 1 is nothing but the homomorphism from uh, N to C. So that's C minus 1. There's another theory behind it. It's the so-called minus 1th Tate twist of this module C. This also can be found in the same reference by the Serre, Merkurjev, and Garibaldi. This just one remark or paragraph. I don't know. So these are called as the so-called residue maps. So, by the way, these maps are surjective, right? Because it's part of that split exercise. So these are the so-called residue maps. Okay. And for some easy cases, some things are easy to check. By the way, this K is basically Hi K comma C is nothing but Hi G comma C. And Hi minus 1 little k is basically the absolute Galois of little k. That's basically gamma, right? So it's really coming from theorem 1. That's what I'm trying to emphasize. Right. So this gamma is basically the absolute Galois of little k. So we're denoting little k here. And that G is again the absolute Galois of big k. So nothing fancy. Right. So now that we have residue maps. So one question you may ask, how does this maps look on cocycles, right? Because you can define the group cohomology using the usual cocycle formulas. So there's a nice description again in that same reference. Without the proof, it's mentioned as a remark in that same reference of Garibaldi, Merkurjev, and Serre that so it's like this. So let's take a normalized cocycle. So if is a normalized I cocycle, so R of F will be a I minus 1 cocycle. It will be a map from gamma to Hom and C. And so what will it be? It's just uh, so gamma is G mod n. So you just or no, sorry, this is not from gamma, it's gamma I minus 1. So what you do, you just take some coset representatives, which I will denote as this, and that will be basically, so that should be a map from N to C. So if you take any element x, that is just f of, so remember f is a normalized cocycle. So it will take I arguments, and these I arguments is just this. There's I minus 1, there is x. There, that's what it is, and there are some few things to check. The well definedness, because we are choosing some representatives of the coset and all, but that can be done, I believe. So one obvious thing is for I is 1. Okay, so for I is 1, the residue maps that is just are the restriction map, right? Obviously, because that is just this hom is just h1 in comma c. Because there's no such this thing, because I is 1, so that's just f of x. Right? So it's the same map with the domain restrict. So that's one nice observation. And another observation that will be really helpful next time, that I would just like to mention here at the end, is that you have a cup product pairing as well. So there is a pairing. So you have a cup product pairing. So that is, you take h1 this thing, then you take hi minus 1 this, and you cup them to get an element here. And then obviously, because it is C, because you have mu and tensor on uh, n comma C. To C. You have a map, right? It's like, okay. And again, by that split exact thing, you can view this sitting inside this, right? Because you just replace C with C minus 1 in that split exact sequence that we get from theorem on part 2. So you can restrict the cup product pairing in the second variable to this, and that will just give me same thing. And that's functorial in K. Okay. So these are the things we'll next time we'll try to specialize C to just mu in, and we'll try to draw some more conclusion that will be really interesting. And from there on we'll move to the next few things, the other residue maps and how they're related and so on.